Sorry, guys. It's just welcome to the life, right? Um, there we go. Respiratory system. These two are awesome. Completely unrelated, the respiratory system and the digestion. And I kind of like that because they're mucho bueno importante. All right? But they're completely different. All right? So you're going to kind of... Let's see how this goes. It's going to be fun. Adult breathing rate is somewhere between 12 to 20 breaths per minute. Okay, respiration occurs basically on two levels. It occurs on a macroscopic level, okay, but it also occurs on a microscopic level. And you're going to see later on something called external respiration, external, as well as internal respiration. Two opposite sides of the same coin, and we'll get into that. Gas exchange of oxygen and carbon dioxide occurs at the cellular and molecular levels. And you see, like, external respiration is the process of my lungs interacting with the outside environment. External respiration, the whole process of oxygen getting into my blood and CO2 getting out of my blood. That oxygen travels around now, you know what I mean? And y'all know where it goes, how to get to the big toe. Isn't knowledge awesome? And the oxygenated blood gets to my big toe. Now the oxygen has got to get from the blood to my big toe, and the carbon dioxide's got to get from my big toe to the blood. This is what we call internal respiration. We'll get there. I'm just rambling on. Yeah, this PowerPoint is about 60 slides, and that's just this one here. So we're going to kind of boogie as best we can. I'm not going to show any videos because y'all have the videos. Watch them. They're mint. They're exactly what you need to process the understanding. And I can't put them in the video. I can't put them in this video because YouTube will take it down for copyright infringement. But y'all have them, okay? Aerobic reactions of cellular respiration allow for ATP production. And you got to think, why are we breathing oxygen? What gas do you need to start a fire to cook and burn your marshmallows? You need oxygen for fire. Well, it's the same thing going on in your tummy when you eat that banana. You're burning it. You're burning it just at a very low temperature. Okay? And instead of fire, because that would be bad, your body takes that fire energy and uses it for muscle movement and all these kinds of good things. Carbon dioxide, you're going to see it doesn't really come back to the lungs as carbon dioxide. Comes back as something carbonic acid, but we'll get there, which your body uses as a blood pH, but we'll get there. Hello to anybody who just joined in. You haven't missed anything. I talk way too much. Let's go. We're on slide 3. Respiration. A couple functions here. Please know these. Functions of the respiratory system. Takes in O2, removes CO2. Absolutely regulates blood pH. You'll know what blood pH is. It's somewhere in between 7.2 and 7.3, 7.4. Anything outside that, you are very sick. Okay? And how the blood regulates the pH is through carbon dioxide returning back to the body. Okay, it's carbonic acid. It acts like a buffer. A buffer, you'll remember that one. The part of the respiratory system there, you know, when it comes through your nose, and I'll show you there, it's coming down your trachea and all this kind of stuff. You've got hairs and mucus, and it's all nice and warm and moist in there and icky. Well, you don't want minus 30 air going into your lungs because then you'll be dead. So the air comes in, it gets warmed up and moistened, and then it goes to the lungs. All right, warms and moistens the air, filters the air. Nose hairs are good for something. There you go. Filters out bacteria, dust particles, these kinds of things. Gives us a sense of smell, which is really just a sense of taste. Produces sound through your vocal cords. Okay, lots of stuff there. Let's go. Respiration involves both the respiratory and the circulatory system. Okay, you'll see these words here. Please know them. Ventilation, inspiration, expiration, respiration, cellular respiration. So you could actually call this one here external respiration, gas exchange. Okay, cellular respiration at the cellular level, oxygen there to make ATP. Okay, expire, breathing out. Inspire, breathing in. Ventilation, moving of air in and out of the lungs. Just to let you guys know that when you take a breath, and I know you're taking a breath because you have to be breathing. You actually think that you're causing that air to go in, you're sucking in the air. It's going to be strange, but your body is just a marvel of cheap labor, and it utilizes whatever it can, and you are not sucking that air in. That air is actually rushing in. Air pressure. And before I begin, air pressure, and you have to think that how does a plane get up in the air? Is it the engines, the wings? How does, a 30-ton, I don't know, how much does a 747 weigh? 20 tons? 50 tons? I have no idea. But let's just say 30 tons. How does a 30-ton airplane get lifted in the air? How does it stay in the air? And it's by air. And if you see here, I have a piece of paper. I'm going to try and angle this. And so if I blow on top of this paper, if I blow air on the top of it, see, right here, see, there's a top and a bottom. If I blow air on top of it, is it going to go up or down? So I'm blowing air on top of it, up or down. Let's have a look here. So you see here, I'm right here. I don't know if you guys can see that or not. I was blowing air on top of the paper, and the paper went up. I'm blowing air on top of it, and the air went up. Weird. And it's the whole thing. You guys will see there that there's a hurricane down in Florida right now. And you'll notice there that high pressure and low pressure. And I'm not going to go into the whole kind of thing about, I'm going to try and just give a quick little version here, but high pressure, and I mean, the air is hitting us right now. Like I'm getting bombarded by, and you are too, by billions of atoms of air right now. And it's pushing on us. All right. And it's pushing on this piece of paper, the same on the top as it is on the bottom. But fast moving air, think hurricane, fast moving air. If anyone watches the Weather Channel, rainy days, low pressure. Hot sunny days, high pressure. High pressure, hot sunny day, no wind. Cold, rainy, wet day, lots of wind, it's cold. Okay, low pressure. Rainy days, low pressure. Sunny days, high pressure. So stormy weather, low pressure. Well, look what's happening here. I don't know if you guys could see that or not, but I created a hurricane on top of the paper, low pressure. The same pressure was underneath. And because I created a low pressure on top, and that's how a 30-ton plane gets in the air. is you'll see the wings on all planes. The top looks like this, the bottom looks like this. And when a plane is on the runway, it's got to hit a certain speed. And when it does, the air pressure on top of the wing goes down. The air pressure underneath stays the same. And therefore now you're a 30-ton plane. So we're going to, in order to do respiration, I apologize, I had to give you guys a little bit of an intro on what air pressure is. Okay? And we're going to get into this a little bit. And it's really good. It's really good. Know these 5 right here: ventilation, inspiration, expiration. Have a look here. There's a couple things here I want to break down. We've got pulmonary ventilation, breathing. Now that should make sense. Pulmonary means lung, ventilation, okay, breathing, movement of the air in and out of the lungs. And this is a part of the respiratory system. External respiration. Okay, this is oxygen and CO2 exchange between the lungs and the blood. We'll get there. So this is technically the respiratory system. But the respiratory system don't work without the circulatory, because the whole point of the respiratory is to get oxygen into the blood and get CO2 out of the blood. Well, now the circulatory system will kick in. So the two of them kind of work like this. All right? And you'll see here there's a bit of a gray area, and now we're into the circulatory system where the blood transports the O2 and CO2. And then we get into internal respiration. This is the exchange of O2 and CO2 to my big toe. And then we have cellular respiration, here ATP production and CO2 production. Okay, so good stuff there, new language. And you see there that your repertoire of knowledge is growing exponentially. All right, and these words here, they are right in your wheelhouse. They are. All right, let's get into it here. I have better shots here, but you'll see here that the respiratory system starts with the nose, and I have better shots here. I'll show you the nasal cavity. You've got sinuses in here, a couple of them. Pharynx, okay, and that stops right here. So right here is considered the upper respiratory, and then everything there below the pharynx, which I'll get into in more detail. So the larynx, the trachea, the lungs, and all this. This is what we consider the lower respiratory tract. Okay, upper, lower. And you'll see all this good stuff in here. Okay, am I going to get you on all this? No. We're going for the main stuff here. All right, and we'll show you guys this there. You'll see there's your nostril. And you see here, you have these nasal conchae. And you've got a superior, middle, and inferior. And you see it's these passageways, right? And this is the body's way of ensuring that if one way is blocked, well, we've got another one. Like you guys remember there in the brain, the circle of Willis. Like what a great, you know what I mean? Like where do you can't write this stuff up. And if some way is going to be blocked, then there's got to be another way. Even there with the capillary sphincters. You know what I mean? If all of a sudden there's an issue on the other side of the body, well, we're going to turn off all these capillaries, get the blood over to the other side of the body, because these guys here will be okay for a minute or two. All right? And love it. What do we got here? I'm just going to zoom in. Okay? Here's your nasal conchae. Okay? You see your nasopharynx. You've got an oropharynx and a laryngopharynx. So you've got 3 pharynx. Okay? Naso, oro, and I say laryngeo, laryngo, however you want to say it. It's not an English course. All right? And then we have the larynx, which is right down here. You'll see here, we see this is, you see you'll have the trachea and the esophagus. All right. And I think I have a better shot of this here. See if I can scroll down just a little bit further. When we do a heart lab there for my pre-health bio class there, the students sometimes they'll get a heart, a porcine heart, and but then there'll be a piece of trachea and a piece of esophagus because they come from the abattoir, right? And some of the hearts will have a piece of trachea and esophagus attached to it. Okay, gross. But I actually tell hey, you guys are the lucky ones. And they kind of look at me like this. I go, yeah, man, feel you guys got a trachea. And I tell all the students in the class, go over and hit this lab over here. Go and see these guys here because they've got a trachea and an esophagus. And you have to think, the esophagus, honestly, it just kind of looks like a breakfast sausage. You know what I mean? It's just small, and it can open up when food comes in, all right? But which we'll get into there for digestion. But then you'll see here, the food comes down here, okay? And then it hits the epiglottis, which is this flap, okay? And then the food travels down the esophagus here, okay? And the air that you breathe coming in through the mouth or the nose, right, comes down and just goes right in here, and the epiglottis doesn't fold down. So the epiglottis is there to make sure that food and water goes down here. And if you've ever, had some popcorn and a little piece gets in here, well, all of a sudden, man, whatever you were doing stops, and now you're in a coughing fit until that piece of popcorn gets out of there, right? So you'll notice there the hyoid bone, okay? That's one of the only bones there that is kind of free floating, doesn't articulate with anything, okay? That's a good one there. Trachea and esophagus. You'll have a look here, pseudostratified columnar epithelium. This is generally what we're talking about here for the respiratory tract. And you see this word right here? Know this one, cilia. This is little hairs on the inside of your lungs. Okay, so there's a reason why your lungs are coated with this pseudostratified columnar epithelium, because it produces, and these goblet cells, which you'll see more of in digestion, okay, but they produce mucus. And what you have here now is you've got this mucousy, hairy environment. It's kind of like seaweed at the bottom of the ocean. You know how it kind of moves like this, right? Well, for dust particles, any type of pollution, smoking, all these kinds of contaminants that can get into the lungs, well, these things, these bugs, even bacteria get trapped in the mucus, okay, and these particles, and then they get pushed out. And then eventually at some point in time, excuse me, I'm going to be a little, that's what the whole point is, right? You got to clean those lungs out. And one of the big problems there with smoking is you end up, after a long period of time, you end up burning those cilia out. So there's no more cilia in the lungs. So therefore now you've got nothing to move that mucus stuff out of the lungs. And so there you have these pools of debris just sitting in your lungs. And depending upon the nature of this debris, you know what I mean, anything can become carcinogenic after a while, all right? So that's just the whole thing. But those are the cells associated there with the respiratory. Your larynx, your voice box. The larynx is enlargement in the airway superior to the trachea, okay? Inferior there to the pharynx. It's composed of a framework of muscles, okay? And you'll have a look here. There's a really good video. Takes a camera down the lungs, and there's also another good video there. It takes a camera down the stomach. So have a look at those ones, man. They're cool. So, and you see here, it's just basically air moving against the larynx, right? And that's our voice box there. Epiglottis. This covers the opening to the larynx so that food doesn't enter into the lower respiratory structures. Not too bad. Here we get into the mucus and the cilia. Excuse me. But I want to zoom in here and have a look at this. So So now we're into the lower respiratory tract, right? So here's my larynx, okay? And what do we got here? You'll see the trachea coming down. And if I can go back to here, and you look at, there's my esophagus, and here's my trachea. The trachea is lined with these, what we call these C-ring cartilage. Okay? There's these cartilage, your nose, right? And so the trachea has protection. The esophagus doesn't. There's a reason why. 5 minutes without air, you're dead. 5 days without food, I can get back into my grade 11 jeans. All right, so that's the difference. So the body is very protective of the esophagus, or sorry, of the trachea. Okay, getting back down into here, and you'll see here are these cartilaginous rings. Okay, so there's your trachea, cartilaginous rings. We'll get more into these here, but you'll see that there are branches that come off. Okay, there's your trachea. Then you got a bronchus. You got a right primary bronchus and a left bronchus. Okay, these are massive. See, they all have the cartilaginous rings. Got to keep those airways open. And we'll get into yeah, we'll get into that. And you'll see how it separates into different bronchus, bronchi, these kinds of things. And it's kind of like the Mississippi again, where you have the big channel, which then goes into smaller ones and smaller ones and smaller ones. And then at the end of the line, we have what's called alveoli. Those are the microscopic, they look like little grapes, you know, like a bunch of grapes. That's what they are. Right, those are at the end of the line, but we'll get there. Okay. You'll have a look here. Here is this cartilaginous ring of the trachea. Okay. Love this word, lumen. Okay. It just means whole. And you think about it there. You're basically your respiratory tract, your upper respiratory and lower respiratory tract is all just one lumen. Even your digestive tract, from rooter to tutor, from mouth to end, is one big lumen. All right, and so I just wanted to show you guys this there, that these cartilaginous rings are there to protect the trachea. Okay. Left and right bronchi. Okay, they enter the lungs and branch into many smaller and smaller bronchioles, and eventually what's called a terminal bronchus. Okay. Alveoli are located at the terminal ends of the bronchioles. Alveoli. I'll show you those in a second. And the terminal bronchioles and alveoli are the main parts of the respiratory zone. So that's where all the good stuff is going to happen. And here's just another shot. Y'all can have a look at this there. Okay. I don't know if it's any better than the other shots, but yeah, there's your larynx, and there's your trachea. There's your right primary, your left primary is over here, and you guys can all have a look at these, okay? And then these are your alveoli, all right? These are at the very end, and you'll see here that you see the air. You know what I mean? You're breathing in, comes in, and in, and in, and in, and in, all the way to the end. And the oxygen comes in here. All right? And these guys here, they are completely surrounded by capillaries. Like it looks like a spider web, completely just a mat of capillaries surrounding these alveoli. And now where are these capillaries coming from? Right? The right ventricle. Right? Coming up. Okay, the pulmonary artery. And it's going right to the lungs. Now, and we spoke about this there when we were doing the heart. The blood coming out of the right ventricle, the pulmonary artery, going to the lungs, like that's massive. It's massive. There's no oxygen exchange going on in these big arteries, right? Oxygen exchange only happens in the capillaries. So you figure the distance from the heart to the lungs ain't very big. So this stuff is coming from the heart, bang, and it slows right down to the capillaries. Capillaries pick up the oxygen from the alveoli. They dump the CO2 into the alveoli. Okay, the blood goes on back to the heart and out the aorta to my big toe, and this CO2 that that the blood put in here now goes out. All right, we're going to go into some more detail, but really not much more. That's what we're looking at right there. And I just put this in because it just kind of looked pretty. All right, and you guys can follow this around and just have a look at it. And the lungs are incredible. Just have a look. That's what they look like. It's incredible. Beautiful. Love it. Yeah, have a look here. Now, I want to before I show you that one, I want to show you this one. This is what I wanted. You see these alveoli here? Okay, these are, terminus bronchus here, and these little grapes here, they're just completely circumvented by capillaries. And these are coming from the heart. Okay, this is coming from the heart. There's your pulmonary artery right here. There's no oxygen, lots of CO2, and then the gas exchange happens here. Blood turns bright red in the presence of oxygen, and out to the left atrium, and away you go. Okay, isn't it amazing? You know what I mean? Just the knowledge there. You guys know the heart now. It's great. I love it. I love it. What else we got here? And again, this is just a micrograph of these alveoli here. Okay, and you can have a look at them there. Oh, I wanted to go back to these ones here. Sorry. So, the structure of the bronchus is similar to that of the trachea, but the C-shaped cartilaginous rings are replaced with cartilaginous plates. So, these rings are basically only for the trachea and the big bronchus. Okay? Once these little guys they don't have the cartilaginous rings anymore. They still have some type of protection. Okay? They have little cartilaginous plates, but really not as much as the trachea or the big bronchus. The respiratory tubes become thinner and thinner until we get to alveoli, and you'll see what goes on here. So I'm just going to put this down here. There we go. And you'll see it's coming from the heart, the oxygen. And you see here, remember this is blood that just came from the vena cava, right? Okay, and it's coming in the right atrium, down to the right ventricle and out the pulmonary artery, and here it comes, right? This low oxygen, high CO2 blood. And you'll see here that this is oxygen in the air. This is from, you just breathe this in. And the oxygen in the air is about 21%. The oxygen in here is really, really low. Really like, zero. Let's call it 0%. And you see the oxygen in here is 21%. So through simple diffusion, free money, the oxygen just jumps here. Free. Doesn't cost the body nothing. And the CO2 out here is greater than the CO2 that's in the air normally. It's about 3%, maybe 1%, 0.3%, somewhere in there. So the CO2 just jumps in easy peasy. So it's all free money. Just some more shots here. There's your alveolar sacs, and you'll see how they all work here. Nothing too crazy. Nice little shot here. Trachea, bronchi, bronchioles, terminal. Okay. What do we got here? Yeah, this is type 1 and type 2 alveolar cells. All right. There are two kinds of alveoli. Okay, right. The respiratory bronchioles and alveoli are the site of gas exchange. We know that. Okay, most of the air-facing surfaces of the wall are lined with type 1. Okay, blood and capillaries is only separated by air. Okay, so the capillaries are circumventing this. The cells cover about 90% of the alveolar surface. So these are the guys here who are taking oxygen and CO2 and exchanging it from the blood to the lungs and back and forth. Type 2 alveolar cells. Okay, these ones here, they produce surfactant. Now, you remember, we're going to get into what happens there, how your lungs, and I'll show you this there, how your lungs expand. And just the whole idea there that air is rushing in. You're not sucking it in. You're not breathing it in. It's rushing in. And it's amazing what happens here, but how the lungs expand. And I kind of alluded to this there a couple of weeks ago. If you take 2 pieces of cellophane, plastic wrap, put them together, you could easily pull them apart. But if you lay one piece of plastic wrap down flat on the table and put like a couple drops of water, and then put the other piece of plastic wrap on top of it, and you know what I mean, squeeze out all the air so it's just 2 pieces on top of, you know, the water in the middle. Not even the Hulk could pull those apart without breaking the cellophane. It's basically an indestructible system, that the only way you're ever going to get these 2 pieces of cellophane apart, it's impossible. There's an enormous amount of suction. And that's how the lungs work. Okay? Do you guys remember your parietal pleura? It's something called a pleura, which we're going to get into there later. And there's linings of the lungs that you have one pleura, you have another pleura, and in the middle you have surfactant. This chemical produced by these type 2 alveolar, okay, that keeps things wet and moist, sticky, and you'll see there keeps keeps it all together. But we'll get there. The total surface area of the alveoli is very large. You'll see this there when we talk about the small intestine. Your body is a master at taking a small space and making it enormous. If you take your lungs and flatten them out to all the surface area available within your lungs, you would have the same surface area in your lungs as you would on an entire tennis court. That's how much surface area is in your lungs. All right? So that's how much air we are capable of breathing. All right? It's amazing. And the small intestine is the same when we get there later today. It's good. What do we got? Aha! Here's our pleura. And these pleura, they're just membranes. And you'll see here that you have what's called your visceral pleura. Okay? Right here. And you see you have your parietal pleura. And this is just a cross-section. Okay? Here's my heart. And looking at this here, you should be able to tell this is my anterior, posterior. Okay? This is my left side, my right side. You see my spinal column right here. Well, it's not mine, but you'll see the orientation. Okay? And you'll see here, these pleura, these are these 2 pieces of cellophane, plastic wrap. Okay? And with a surfactant in the middle. So when you expand your lungs out this way, like you do every time you take a breath, this pleura comes with the body, and this pleura here comes by suction. And if this pleura comes here by suction, then the lungs are going to go with it too. So you see how it works? You breathe in, you expand your thoracic cavity. Okay, these pleura go with it, and in the process, take your lungs with it too, so that your lungs are able to expand. Because your lungs aren't a muscle, they're an organ, right? They get kind of told what to do. So there's your visceral pleura, your parietal pleura. Surfactant, type 1, type 2 alveolar cells. Okay? Interesting to note there, the right lung has 3 lobes. Left lung has 2. And you'll see here that the left lung is actually a little smaller. Okay, right lung has 3 lobes, this one has 2. This one here's got a little notch called the cardiac notch. Did I miss something here? Yeah, have a look at this there. It just goes into a little bit about the visceral and parietal pleura. Have a look at those there. Lungs, they're damaged by smoking. And you'll see there that you get this spotting. Okay. You'll have a look here. These are, you see all the capillaries. Like this is a real electron micrograph. Okay. There's your alveoli. There's all your capillaries all around. Okay. And then in a smoking situation there, we have, you know what I mean? You have pitting and spotting and all that kind of stuff. Just another shot. I like this one here. Demonstrates, there's your lymph again. Your lymph is all over the place. Okay, but here's your capillaries there coming right from the heart, and they're there to receive oxygen and dump off there the CO2. Okay. Inspiration. Okay, so atmospheric pressure. All right, there's, and I'm not really going to go into the mathematics. If you guys do decide, and I hope you guys do, I'll pester you guys, and you go on and get a nursing degree. Go on and get a bachelor and a master's. Go. You guys can do it. You guys can do this. You guys can do anything. Swear to God. Believe in yourself. This is kind of the American system, 760 millimeters of mercury. Here in Canada, we use kPa, kilopascals. That is a normal sunny day. That is normal atmospheric pressure. Okay? 24 degrees, 25 degrees, the sun's shining, it's nice. That's a normal day. 101.3 kPa, which can also, the Americans and the Brits, they use millimeters of mercury. Okay? And it all means the same thing. There's actually one there that we use for science. It's called atmospheres. One atmosphere. They all mean the same thing. They all mean normal pressure. Okay, they all mean the same number. So, but we'll use the American system here. It's fine. So, a normal day atmospheric pressure. I really got to move that somewhere else. There we go. So, atmospheric pressure is always basically 760 millimeters of mercury. Or here in Canada, we use 101.3 kPa, kilopascals. Okay, so the air comes in, it's always at a certain pressure. And we talked about that, right? Remember your piece of paper? The pressure here is the same as the pressure here. Everything's good. But if I change the pressure, okay, which we can do, right? But for all intents and purposes, the outside air is 760 millimeters of mercury. Your lungs are not. They are either a little below 760 millimeters of mercury or a little higher than 760 millimeters of mercury. But they are never 760 millimeters. Your lungs are never at the same air pressure as the outside. Okay? There's a reason for that. Because if our lungs were the same pressure as the outside, well, the air's not going to go anywhere. You see, I got air right here in my hand, and I got air right here in my hand. Okay, well, it's all the same. It has no need to go anywhere. Things go from a high to a low. Always. For free energy. Yeah, talk to me.
Questions in regards to how you would maybe word this on a test. Would you use the kPa or would you use the mercury?
I'm not going to do any mathematics. Like where you guys are going, they will probably use this one here in the medical field. 700. That's normal atmospheric pressure. You see, like today, I don't know, here in Barrie, it's kind of cloudy. It's probably spitting a bit. You know, I'd probably say it's maybe 755 millimeters of mercury there today because it's a little lower pressure. It's kind of rainy. It's not a nice day. But I wouldn't give you guys any math questions. This one here, I didn't. Go ahead.
Would there be a question like, what is the average atmospheric pressure? Would you like? For an answer, would you be more willing to put the mercury or?
That is a great question.
Like, I know multiple choice questions like that would be the case.
Know these three numbers, And all of them mean the same thing. This one here, the entire world uses. This one here, only England, the UK, America, and I think the Ivory Coast is another one there that sticks to the imperial system. And I don't know, there's only a handful of countries in the world that still use it. And this one here is more scientific. Venus has a pressure of, I think it's 5 or 6 atmospheres. Like, it's just massive pressure. The moon has a pressure of, I think, about 0.2 atmospheres. But all of these mean the same. Just know that, yeah, that's a great question. What would be considered normal atmospheric pressure? And I could give you either one of these 3, and there you go. You know what I mean? But good question. Did I answer it?
Yeah.
Okay. All right. So very, very important here. Your lungs are never atmospheric pressure. If you're on an ATV and you get thrown from your ATV and you land on a fence post, which I've read about, we've seen it, and Buddy's got a punctured lung, where the fence has gone right through his lung. Okay? It's called a pneumothorax. Right? And what's happened now, the lung is the same pressure, because there's a hole in your chest, okay? And the lung is now the same pressure as outside, because there's a hole in your chest, so the lung is just like basically a deflated balloon, right? A punctured lung. That's what that means, right? And the whole brilliance behind the lungs is that they're just above atmospheric pressure or just below. And I'll show you why. Have a look here of this one. And, like a hypodermic needle here. If the plunger was closed, right, and you want to draw in fluid or air or whatever, right, and you pull the plunger back, and it causes this kind of negative pressure. So the pressure in here is now way less than the pressure outside. So what happens? The air just rushes in as you draw that plunger back. It rushes in because you've allowed space in here for the air to go. So the air is going to go in there. Same as your lungs. You breathe in. You've now drawing that plunger down. So the air, whether you like it or not, it's going in. So you think you have control over your breathing. It is what it is, right? It was my daughter there. She was upset. Well, I'm going to hold my breath. All right, just make sure you do it sitting down. Okay, I'm going to hold my breath. You know what I mean? And, whether they pass out in 5 seconds, they'll start breathing again. So, and you hear the opposite there when you breathe out. Remember your lungs, and you breathe out. You've now made a smaller space inside your thoracic cavity. So the pressure in here is greater than the pressure out here. So you're not pushing the air out. The air is just getting out of Dodge. So it all has to do with the volume, your space, your capacity, right? And you see, lower pressure inside, air rushes in. Higher pressure inside, air rushes out. That's the lungs. Okay. The videos, maybe I'm not explaining as well as I could. It's been a rough day already, but the videos are mint. They'll just take care of that. This has to do with something, Boyle's law. And this law right here is all based on the lungs. And it's pressure times volume. I'm not going to ask you guys this, all right? But you guys will see this again, I promise, in other courses. Boyle's law. Pressure times volume is relative to pressure times volume. And you'll see here. Here I've got this container. And you know what I mean? It's kind of like the same thing as the hypodermic needle. And you see, air pressure, like the whole idea that this goes up. What is pushing it up? Well, it's the air molecules. And you see they're banging around, bang, 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 and they're just hitting the sides of the container. That's why a balloon takes that shape, because the atoms, molecules in the inside are whacking the inside of the balloon. And that's what's going on here. And you see these guys? Okay, so I got a kind of a big volume here. These guys are just, they're banging around. They got elbow room. Okay, so the pressure here isn't that good. And just think of these as people. Let's say I have 1, 2, 3, 4, 5 people in the living room. Everyone's got elbow room. Everyone's doing all right. Low pressure. So big volume, low pressure. You see how it works like this? Big volume, low pressure. What happens if I put the plunger down? My volume has gone down. My pressure has gone up. Boyle's law works inversely. So if you had 5 people in the living room, everyone's comfortable, low pressure. You put the same 5 people in the bathroom, well, people are going to start to get pretty mad. All right? So that's how this one works. And it's called Boyle's law. And this is how the lungs do this for free. It's awesome. These are the muscles there that are involved in inhaling and exhaling. Okay? I know we did muscles there a while ago and all this kind of stuff. But you'll see there now, we're at the level of the game now where now different chapters, everything comes together. Okay? I don't know, I might ask you some. I have some more over here. But you'll have a look here. You'll see how it, when you're breathing in, have a look here of what the motion is. There's up and out and down. All right? The whole thing is expanding. How does it do this? The diaphragm. Okay? The diaphragm is this bell-shaped muscle. Okay? It kind of separates there the upper thorax from the lower thorax, right? There's your diaphragm, and that's at rest. But when you breathe in, what happens is the diaphragm goes down. And when the diaphragm goes down, what have you done to your thorax? You've expanded it. Air rushes in. Pressure's lower, high pressure to low. Okay, again, diaphragm, it's a bell-shaped muscle like this, and it's at rest like this. You breathe in, goes down, lungs expand, air comes in. Breathe out, and the thorax gets smaller. Okay? Breathing in, breathing out. Breathing in, breathing out. That's your diaphragm right in here. Okay? And you'll see there, it's the opposite there for your exhalation. Easy peasy. Not too bad. You guys can have a look at this there. Major events and inspiration. Okay, your phrenic nerve. Okay, it's all controlled. We do have control. Like, when we sleep, we're not conscious, but we're still breathing, right? So there has to be some type of autonomic function going on here, right? Computerized. This thing is on automatic. But you see, we do have control over some of our breathing. I can just pretend to hyperventilate, right? Okay? But eventually, you're either going to pass out or get bored of it, or, you know what I mean, your macaroni and cheese is going to be done on the stove, so you're going to stop hyperventilating, and then you're just going to go back to normal, back to your autonomic nervous system. So this is it's awesome. As the dome-shaped diaphragm moves downward, the thoracic cavity expands. At the same time, the external intercostal muscles may contract, raising the rib cage. Okay, the intraalveolar pressure decreases. Atmospheric pressure, greater on the outside, forces air to come on into the lungs. The lungs fill with air. Brilliant slide. The opposite. Okay, diaphragm and the external respiratory muscles, relax. Okay, the elastic tissue of the lungs and thoracic cage, they go back to normal. They recoil. The amount of volume in the lungs decreases, air is squeezed out because the pressure inside the lungs is bigger than the pressure outside. Okay, good. Pulmonary ventilation. How does this relate to lungs? A volume change would lead to a pressure change. Of course it does. Volume, pressure. Know that. When the volume increases, what happens to my pressure? Decreases. When my volume decreases, pressure increases. And just think about it. If you have 5 people in a room, move them to the bathroom, pressure will increase. They'll be really mad. Okay. The pressure changes lead to a flow of gas. And this is why the lungs are never at atmospheric pressure. Like I told you there before, if you have the same atmospheric pressure, gases ain't going to flow. But if you have a difference, why do you think we have wind? Air that is at a high pressure system somewhere, I don't know, maybe Saskatchewan, and a pocket of air over Manitoba is low pressure. Well, where do you think the air is going to go? It's going to flow high to a low to equalize the pressure. Pulmonary ventilation, defined as the exchange of air between the atmosphere and alveoli. Air always flows towards lower pressure. Okay, since atmospheric pressure is fairly constant, this means the airflow depends on the pressure inside of the lungs. Okay, the lungs are always going to be off. Just a little under, a little over. Sea level 160 millimeters of mercury or 1 atmosphere. We've gone through this. Oh, by the way, boiling point of water is 100 degrees Celsius, right? Not if you're on Mount Everest. Air pressure plays a major factor in boiling temperatures because you have a glass of water, right? Let's say I start to have heat, and what is stopping this water from boiling off and flying off into space? Air pressure. It's forcing it down. And eventually, if I keep adding fire to it, it will be stronger than the air pressure, and then it'll start to boil. That's how it works. Well, if you're on the top of Mount Everest, you are now 8 kilometers up into the air. There's not a lot of air up there, which means there's not a lot of air pressure up there, which means that your water doesn't boil at 100 degrees Celsius. I'll let you find that out. Quick Google search, and there you go. Water doesn't boil at 100 degrees Celsius on top of Mount Everest because there's not a lot of air to hold that water down. So you don't need as much fire. Water doesn't boil at 100 degrees Celsius on top of Everest. Find it out. I think it's somewhere in the 70s. All right. Pulmonary ventilation during inhalation, what happens? Okay, we've gone through this already. Have a read of it there, just the whole idea of pressure change. You guys are on that. Interpleural pressure. Okay. Pleural, those are those cellophane plastic wraps there that surround the lungs. Okay, the little spaces in there. Your interpleural pressure also fluctuates with breathing. Okay, but it's a little off from the alveolar pressure. I'll show you some slides there later on. What's going on here? That's what I'm looking for. And you'll see here, it's the same thing. And I want to start, where do I want to start? Okay, so at rest. Actually, I don't want to start at rest. Here I'm breathing in. Here we're at this slide right here. I'm breathing in. Atmospheric pressure is 760 millimeters of mercury. Inside, okay, it's 754. Your alveolar pressure is 757. So you see there that these guys are a little off, but what you need to know is that the difference between these two and these two here, these guys are a little less. So higher pressure outside, lower pressure inside. Exhalation here, you'll see atmospheric pressure 760. Okay, you'll see your interpleural pressure really doesn't change that much. It's the alveolar pressure, and you'll see, have a look there. It's now just a little bit bigger than atmospheric pressure. Blows out. Okay, neat little slide. Interesting to note there that these are the percentages of the main gases that's in our air. Okay, the major constituent of our air is nitrogen. Okay, N2, and it's about 78% of all of our air is nitrogen. It's a neutral, you know what I mean? It's not flammable. It's just there. It's completely inert. Oxygen is about 21%, which is pretty big, man. That's a lot of oxygen. That's 1 in every 5 molecules is oxygen. So it's pretty high concentration. And you'll notice here your carbon dioxide percentage. There's about 0.03% of our air is carbon dioxide. Okay? So you think about the ramifications for this. The oxygen in the air is 21%. The oxygen in the coming up the vena cava is pretty low. So 21% to 0, this oxygen is going to readily jump right onto the blood. And the carbon dioxide there in the vena cava is pretty high. I think it's about 2%, 3%, which is a lot higher than carbon dioxide that's in the air. So the carbon dioxide easily jumps from the lungs to the air, no problemo. Okay? What do we got here? And this just kind of goes into partial pressure, and I'm not going to go into too much detail on this. It's a famous law. It's called Dalton's law of partial pressure. And the pressure, like let's say I have a balloon here, okay, and this balloon is filled with air, but we now know that air is composed of nitrogen, oxygen, argon, carbon dioxide, methane, all these different things. And depending upon the concentration, the amounts, the pressure will be corresponding. And you'll see here that nitrogen is 78% of all air. So therefore, the air inside of a balloon, the pressure inside of a balloon, 78% of the pressure is nitrogen. The pressure inside of a balloon, 21% of it is from oxygen. And how do we know this? Just from their concentrations. So the concentration of a gas is directly related to the amount of pressure it gives. And we'll get more into this there further on. Right here. So you have a look at this one right here. Normal air pressure, 760 millimeters of mercury, or 1 atmosphere. Actually, or I'm just going to put this in or 101.3 kPa, which means I'll need to make another column. But you'll see here, same table as you saw there before, same percentages as you saw there before, but based on this, normal atmospheric pressure, if nitrogen is 78% of all air, well then 78% of the pressure comes from nitrogen. So all I did was I took 0.78 times this number, and I got this. If oxygen is 21%, then it will be 21% of the pressure. And 21% of 760 is 158. There might be a little calculation or something like that, but I really can't see anything to mathematics. I kind of want to stay away from mathematics. I'm more into understanding. So I don't think you'll need a calculator or anything like this for the final exam. It's too late in the game to start adjusting things now. But definitely these slides here about pressure and gases, a little bit of chemistry there. I don't think it'll hurt you. All right, so just have these slides available there for test day. And you guys, you think about it, eh? We only have one more test. That's it after today. And awesome. Awesome. You guys are just doing great. Gas exchange and transport. It just goes into more of Dalton's law. And I want to show you guys right here. You'll have a look. And you got your systemic system here, and then you got your pulmonary system here. So this is blood that's going to my big toe, and then drops off oxygen there to my big toe, picks up carbon dioxide, goes back to the heart, goes back to the lungs, okay, and then comes around again. So there's two different things going on here. Okay, there's your external respiration, but then right in here we have the internal respiration where the oxygen and carbon dioxide is exchanged. This is a good one, okay? You guys will remember there that, acids and bases, right? Acids, generally weak acids, weak bases aren't too bad, okay? Lemon juice, vinegar, these things make your French fries taste yummy. But then if we get to, extreme pHs of 1 and 2 and, or for acids, or 13 and 14 there for bases, they can be dangerous, right? So pH is a big problem in the blood because the blood is just not one thing. We've seen there, we've done the blood, it's 100 different things. You got antibodies, you got RBCs, you got white BCs, you got plasma, platelets, fibrinogen, mast cells, you know what I mean? It's just a Caesar salad of stuff. And it has to be monitored, okay, as far as pH. Because when we talked about pH being, you know what I mean, there's very little wiggle room for pH variance in the blood, okay? And how body, in my big toe picked up the oxygen and dumped the CO2 into the blood. And now it's going up the, veins, the vena cava, and out, right? Well, on that way, what happens is there's an enzyme called carbonic anhydrase. This is an enzyme, okay, that changes carbon dioxide into bicarbonate. Sodium bicarbonate, baking soda, right? We've all done that there as a kid. You mix baking soda and vinegar and you get yourself a volcano, right? It's a base. It's a weak base. You can eat it. It's not bad for you. And what happens is the carbon dioxide gets changed into bicarbonate ions, okay, which look like this. HCO3. And what happens is now, this can, if there's acids or any issues going on route to the lungs, it can deal, it's a buffer. It maintains that blood pH. And yeah, the CO2, it's on its way out. It's trash. But the use of this enzyme, carbonic anhydrase, gives the CO2, this trash going to the garbage, actually gives it an immensely important purpose and maintaining blood pH there. Okay, right here. Interesting stuff. What do we got here? You remember the pressure we were talking about? And when we go PO2, that's the partial pressure. Okay, because in air, there's 10 different gases, right? I don't really care about the other 8. The only 2 gases I care about right now, because I'm doing respiration, is oxygen and carbon dioxide. So the pressure of the oxygen in the air is about 104 millimeters of mercury. The pressure of the CO2 in the alveoli is 40. Have a look what's going on. This is coming up the vena cava, right? All right. This is the pulmonary artery. It just came out the right ventricle, and it's going to the lungs to pick up oxygen. See, there's not a lot of oxygen in here. There's a lot of CO2 in here. Comes to the alveoli. Have a look at the pressure of the oxygen in the blood here. It's 40. Pressure of oxygen in the air in the alveoli is 104. So this oxygen here is going to jump easy peasy because it's 104 here, 40 in the blood. The CO2 in the blood is 45. The pressure of the CO2 in the alveoli is 40. This is higher than here, so the CO2 jumps. That's a great little slide there. Okay, and guys, please ask questions. I can't see if anyone's there, but if you guys gotta go, go. All right, go and do your test. Go and take care of things. These videos here will be posted there to YouTube. We're getting on the tail end of this one. Told you there today would be a long one, but we'll take a 10-15 minute break in between, and we'll get back and we'll do. Hey, if you have a question, Esther, talk. Shoot it up.
Not related to this. Just wanted to know. I've done the assignment.
Hi, Esther. If this is complete, go ahead.
Load just that page with all the answers, and I uploaded onto the assignment page the whole thing plus the answers on that last page. I apologize.
Hi, can you email this to me, and we'll talk through that, because this stuff is pretty heavy, and I just want to kind of maintain a focus on this. And if we can,
sorry, yep.
Okay, all right, because you're cutting out too, so maybe it's better just chat by typing. Thanks, Esther. But I do want to read that email, so send that to me, or send me an email, please, and whatever it is, we'll sort it out. I promise, it's all good. What do we got here now? Hello. Okay, everyone's mic's off. Okay, good. And you'll see where we are now. You see, this was the external respiration, right? Well, here we've got the opposite end. This is in my big toe. And this is blood coming there from the left ventricle, out the aorta, down the ascending and descending, or sorry, not up the, no, we're going down the descending. So here's my big toe, and you'll see there the oxygen in the capillaries there is 95. That's the pressure of the oxygen in the capillaries. The pressure of the oxygen there in the cells. Hi guys, if you could turn your mics off. Turn your mics on if you have a question, but thank you. And you'll see here it works the same way. The pressure is greater, that will jump. And that's all this. So this is what goes on there in the big toe. All right, and good stuff. What else we got? Hello? And this is just another shot here. Here we've got type 2 and type 1. Okay? And you guys can have a look at this there. You'll remember there that... hi, Esther. I think your microphone's on. If you could just turn that off, that would be great. So you'll remember... Thank you. And you'll see there that the type 2 there, if you remember, they secrete surfactant. And you guys can have a look at this there. Type 1, these are your, where 90% of the alveoli, simple squamous epithelium. Okay. Diffusion. This is kind of overkill. Sorry, it's the same thing. Higher pressure jumps to a lower pressure. And I've included these slides here. If you didn't like this one, then hopefully you like this one. Okay. Oxygen transport. Almost all oxygen carried to the blood is bound to hemoglobin. Okay, chemical bonds there between the O2 and hemoglobin are relatively unstable. Oxyhemoglobin. Okay, I like that. Okay. Carbon dioxide is transported there by, you'll remember the enzyme that changes it into a bicarbonate ion. So there are 3 ways there that CO2 can be taken back to the lungs. Number 1, CO2. Easy peasy. Okay, it can also travel with the hemoglobin, and it's called what was it? Carbamino hemoglobin. Okay, sometimes called carboxy hemoglobin. It can also be transformed into bicarbonate ion, and this is the form there that assists in the regulation of pH. Okay, and so there's 3 ways that CO2 can go back: as CO2, with the hemoglobin, or as bicarbonate. And there's your enzyme there, carbonic anhydrase. Okay, so it's all there. What else we got? And if you guys are working away at this, it's all good. The video will be posted. And I see you guys. Yep, have a look here. Oxygen combines with changes there into oxyhemoglobin. Okay, so the oxygen binds to the iron, which is in the hemoglobin, turns into oxyhemoglobin. Carbon dioxide can be transported back as carbon dioxide, about 7%. Carbon dioxide can be changed, can be attached to the hemoglobin. It's called carbamino hemoglobin. It's the same slide as what we just saw right up in here, but we've got some percentages now. And then here, about 70% of the carbon dioxide comes back as bicarbonate. So 3 different ways there CO2 can go back. Regulation of breathing. You guys should be on this there with your nervous. Okay, main regulatory center is the medulla oblongata. You guys will, I'm sure, be familiar with dorsal and ventral. Okay, right? Okay, your dorsal respiratory group, DRG, signals inspiratory muscles via the phrenic nerve. And we've seen the diaphragm and the intercostals there. Right? You guys have those muscles there. Ventral respiratory group, VRG, sets the rhythm, the pacemaker. So my daughter can be as mad as a hornet and hold her breath all she wants, but eventually her breathing will return. Okay? You guys can have a look at this there. Regulation of breathing. Here we've got the pons, the lower pons. You guys are all on that. Neural control of breathing. And one of the things there that I'm not going to go into, but I'll say a little bit about, is that our autonomic nervous system, we have abilities to kind of like almost the Matrix, where we can jump in, take control, and then jump back out again. And if you want to hold your breath, these kinds of things, you do have control. But eventually, things just go back to being regulated. You look at the limbic system there, there's laughing, there's crying, there's all these hiccups. You know what I mean? We still don't even know what hiccups are all about. So lots of fun, lots of fun. What else we got here? This is where I want to get into, there are several key triggers there for breathing as well. Okay, irritation. Okay, like if a piece of popcorn gets caught or something like that. You've got COPD. Okay, which we'll talk, and these obstructive airway disorders, okay, where the lining of the bronchi can become irritated and rough. Asthma, we'll talk about these there before the PowerPoint's done. Can signal to slow breathing down. Temperature, increased body temperature leads to increased rates of breathing, okay, just to keep things going. Blood vessels expand. We want to cool things down, right? Circulatory is all about thermostat, right? Circulatory and respiration are two sides of the same coin. So if the circulation is speeding up, well, you're breathing better too. Medications, sure. General anesthetic, that knocks you out. Morphine, alcohol, these are all depressants, slow things down, okay? You got the opposite there, amphetamines, caffeine, nicotine, all these are stimulants, right? They're vasodilators, get things moving. Okay. Sorry. What did I do to it? Blood levels of O2 and CO2 and when I say H plus here, I mean acid. So you guys will know there that with the heart, there's the baroreceptors, the chemoreceptors, and one of the main receptors there in the aorta is measuring the CO2 levels, not the O2. Funny enough, it's the CO2, because the amount of O2 levels, not a problemo. The amount of CO2 levels will become poisonous. That's astronauts in space. That's the number one problem is CO2 poisoning. Okay. Yeah. You've got these stretch receptors, peripheral chemoreceptors. We kind of touched on these there with the heart. Y'all can have a look at these. And there's your phrenic nerve. Good word there that you may see again. It's a medical term for stimulate. It's called innervate. Okay, so the phrenic nerve innervates the diaphragm. So the phrenic nerve stimulates, controls the diaphragm. Okay. Regulation of breathing. This is a really good little slide here. Have a look at it. I'm not going into it, but this is a good little one right here. Regulation of breathing. Actually, maybe I will. Exercise. Number 1, oxygen used and carbon dioxide is produced. You breathe in oxygen and there are 2 products, ATP and CO2. Well, actually water too. Chemoreceptors detect blood. So I'll zoom in here. So you just did some exercise, you've used some oxygen, you produce some CO2. The chemoreceptors detect blood O2 and CO2 levels. Okay, these are the receptors there. Sensory information is sent to the medulla oblongata. The medulla signals inspiratory muscles. Increased rate and depth of breathing. So when you got too much CO2, that's the difference between a 100-meter sprinter and a 400-meter sprinter. A 100-meter sprinter, you remember, is myoglobins. The muscles there, they have their own RBCs, right? And there's in the muscles there is a supply of oxygen and sugar ready to go right now. You could run 100 meters without even batting an eye, all of you right now, because you have that stored up. But once that's gone, the oxygen levels have dropped, the CO2 levels have increased, the receptors there send a message there to medulla. Look, we've got CO2 too much in the blood. All right, medulla tells the lungs, get it out of here. Okay? And there's that homeostasis again. It's all like this. And it's always monitored. It's never like this. It's always monitored. The body's always on the tips of its toes. Okay? Always monitoring. Negative feedback control. We took that way back, I think, week 2. It's all coming back. Negative feedback. I would know. Actually, you know what? I really like this slide. You should. What do we got here? Regulation of breathing, coughing, and sneezing. Why do we cough? All right. We get stuff in the trachea and lungs. The mucus can't get out. Irritants, allergies. Big one there. If you have bad allergies to bee stings, peanuts, these kinds of things, boy, man, the airway, your trachea can just get blocked right off. That is a bad one. Okay, that's probably the number 1 problem there, is that the swelling happens, so it blocks off the trachea. Why do we sneeze? Irritants. Again, this is your medulla. Your medulla is involved in sneezing. Okay. Boy, those kids have been alone for an hour and a half. I wonder what my living room looks like now. All right, COPD, and you'll notice there for the heart test. If you've done it or haven't, you know what I mean. You guys will see what it's all about. But some of these are here. You will see these, and you need. Yes, Shire.
Holly pooped and peed downstairs.
Well, thank you for telling me. That's great. Now get out of here.
Well, you come downstairs
I'm teaching. I gotta go. All right. Bye.
Only poop the big one.
Thank you, Shire. That's wonderful. That's great. Oh, yeah, I know. Dad issues. Dad has issues. There you go. All right. COPD, and I've always said there that I'm not really going to focus on the disease aspect, but these ones here, I don't have a choice, man. Y'all are going to see these. Okay. COPD is called chronic obstructive pulmonary disease. Emphysema, chronic bronchitis. Okay. From smoking. That's what this is. And it's just the airwaves. And I think I have some pictures there of damaged airways where, like you remember we were talking there about the blood vessels and how they are they're smooth muscle, right? They're elastic. The arteries are elastic and all this. Well, smoking takes that away, takes that elasticity away. And it happens the same thing in the lungs. And when the bronchioles, the bronchus, when they've lost that ability to that elastic quality, what happens is now they've lost that stretch. So therefore now you got to breathe deeper to get the same amount of air because the amount of surface area in the lungs isn't what it used to be because it's damaged. All right. So what happens is over the course, old smokers, these kinds of things will happen is you'll get what's called a barrel chest because you have to keep breathing in more. Okay. These are all signs of COPD. We've got emphysema here caused by the destruction and collapse of smaller airways, loss of elasticity. Okay. Chronic bronchitis, characterized by excessive mucus production in the bronchi and chronic inflammation. Okay? You do not want to get those bronchi irritated, man. They get red, scratchy, irritated, inflamed. And when things get inflamed, they start to swell. And when your bronchi start to swell, then all of a sudden now the lumen isn't as big as it used to be. And if the lumen ain't as big as it used to be, you can't get as much air. Okay? And that's why you see people take those puffers, right? It's a steroid. It's a listen to this one. These puffer is a steroid. It's a vasodilator. Should know that one. A vasodilator. Okay? Opens things up. Gets things moving again. Sorry, it's a long one, but this is all good stuff, man. We just can't get away from it here. Have a look here. Here is a beautiful pink, healthy alveoli. Okay, alveoli there with COPD, and I'll zoom in a little bit here. Okay, what the heck is that? Mucus accumulates in the bronchi. As I said there, if these guys here don't have any cilia, then that mucus has no way of getting out. And then that mucus just kind of pools and collects bugs, bacteria, cancer stuff, you know what I mean? And you'll see here the alveoli there become damaged, resulting in larger and fewer alveoli. So you see here, see these little grapes here? Bang, 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 bang. Well, now you've got some of the alveoli are damaged. So now they're bigger, okay, and they're less effective. So they have to breathe in more. So that's COPD in a nutshell. Asthma, disease characterized by the intermittent episodes with, in which airway smooth muscle contracts strongly, increasing airway resistance. The basic defect in asthma is chronic inflammation. And I think it's the next slide that I want to show you here. Yeah. This is what I wanted. Have a look at this one. There's a normal bronchi. Okay. Pink. Elastic. Stretchable. You know what I mean? Tough. And then you have this here, bronchiole there with asthma. Like, man, that's not even close. Right? And not only... You see, this is all inflammation, right? It's all rough and irritated because all the blood is going here to try and fix this irritation, right? That's what the blood does. If there's a problem in my big toe, turn on the capillary sphincters, get the blood to my big toe. Well, that's what's going on here. But with this chronic asthma, can't get rid of it. It's a bad one. And they use these steroids there to try and open them up. But you'll see there, it even has mucus in the inside. And what kind of airflow are you going to get through that? Okay. Again, lots of information, COPD and asthma. There are anti-inflammatory drugs. I like that word too. Anti-inflammatory drugs. Tylenol, Panadol, aspirin, ibuprofen. These are all anti-inflame drugs. They take away the inflammation. Okay. Vasodilators, also called bronchodilators. Bronchodilators. Okay. Specifically for the lungs. Bronchodilators. Lifespan changes. The cilia become, this is over time, you know, for people, older people. Okay. And these are just some of the things you're going to see. The cilia become less active or not involved. Mucus thickening, swallowing, gagging, coughing reflex. Okay. There's that barrel chest. Okay. The bronchial walls become thin, collapsed. And this is a big problem, is dead space in the lungs. And you want to try and... We do have air in our lungs that never leaves. And that's just another evolutionary survival tactic by the body, that if I knock my head unconscious and I'm out there and I'm not breathing, there is maybe a 30-second supply, maybe 20 seconds. There's something in there that the body will use to give it some time. All right? But if you have too much dead space, that's a problem. Yeah, we've got that there. Asphyxia, hypoxia, anoxia. Please know those three. Okay. And this one here, I'm not going to go too crazy on. This is, where they hook you up to a machine. Okay. And they measure your breathing rates. And I just wanted to show you this. I don't think I'm going to go to, there's a couple of interesting things on here. But you can see here that this is your total, you break it all down. This is your total lung capacity. But have a look. This is our normal breathing right in here. That's all we breathe and when we're breathing normally. Okay? And inspiratory reserve. And you see, if you just take a breath normally, I'm just breathing normally. Take a breath in normally. You can take more in if you want to. Even though I just took a breath in. And if I take a normal breath out, you can push more out. And you'll see here, we call this your expiratory volume. There's something called your residual volume. There's all these different capacities that are involved in your lungs, even though we only, on a regular basis, we only use this amount for regular breathing. But there is extra volume in there because if a black bear attacks you, you're going to need it. But other than that, that is where we're at. That is the end of that PowerPoint slide. Apologies on the an hour 40 minutes. That's where we're at. Let's meet back here at what, 1:40? Should we meet back here? I don't know. I'd say 10 minutes, but that was kind of long. Should we meet back here at 2 o'clock? Is that too long? Is that all right? Or okay, 10 minutes. Let's go for 10 minutes. And so we'll meet you guys back here at 1:50. Okay? Bye, guys. I'm going to stop the video, but I'm going to keep the PowerPoint open. All right, so we'll see you guys in a bit.